So our first speaker is a pioneer in continuous delivery, a thought leader and expert practitioner of CD, DevOps, TDD, and software development in general. He is the co-author of the Jolt award-winning book, Continuous Delivery. He built one of the world's fastest financial exchanges, is a pioneer of BDD, an author of the Reactive Manifesto, and a winner of the Duke Award for open source software with LMAX Disruptors. The title of his presentation, Engineering for Software, How to Amplify Creativity. Please give a big virtual welcome to David Farley.
Thank you. Welcome, everybody. So today I'd like to talk about engineering for software. And I think that one of the starting points is to think about what does this really mean? What do we think of when we're talking about software engineering? I think many of us probably assume that engineering doesn't really fit very well for what it is that we do. Software isn't, we don't think of it in those terms. But I'd like to try and change your mind. One of the things that we often think about when we think in terms of what engineering may mean is that engineering is the kind of stuff that we can't really afford to get wrong. Things like these. And for physical things, this is probably true. This is probably the case, but this isn't true for our kind of stuff. This is not really the nature of our problem. In software, our products are very different. They are much more malleable. The things that we produce are really always end up as a sequence of bytes. And any system, however complicated that system may be, is represented by a stream of bytes. And one of the unique attributes of computers and information systems is that we can clone any sequence of bytes for essentially free. So we don't have a production problem in our discipline. Our discipline is never one of production. It's always one of the creation of that sequence of bytes in the first place. We can always just, at the push of a button, in essence, just copy our work. We can recreate entire systems essentially for free. What this means is that many of the assumptions that we think of from traditional engineering don't affect us, or they shouldn't if we organize our work correctly. If we think about things like building bridges, then getting the logistics of getting the materials into place are important. The organization of getting the right people and the right stuff in, at the right point in time is a fundamental part of solving the problem. But that's not our problem. We don't have that problem. Another way of thinking about engineering is as a means of discovery. Thinking in terms of engineering as a way of solving practical problems. So applying scientifically rational lines of thinking to solving practical problems. And one of the best examples that I can think of at the moment that's kind of publicly visible is this. This is the prototype of the Starship that Elon Musk and SpaceX are building in Texas at the moment. And the ultimate goal for this thing is to end up by being able to land people on Mars and allow people to live on Mars. And this is also, from an engineering nerd's point of view like me, is a practical demonstration of what leading edge engineering really looks like. So it's not some form of bureaucratic Gantt chart driven effort in logistics. There's certainly part of that, but even for physical devices as complicated as a spaceship, we're going to be trying out pieces of the system in isolation from other pieces and evaluating them and figuring out how we can control the variables so we can measure these things and understand in more depth. And we're going to get things wrong. They're going to explode from time to time. And sometimes we might want to do that on purpose to see what works and what doesn't. Other times we'll build little test pieces that will be able to allow us to evaluate parts of the system and understand what's going on. And still, we're going to get things wrong from time to time. This is what real engineering looks like. We make progress through theory, experiment, learning, making mistakes, and we adapt to all of these things as we go. And this is really fundamentally what engineering for new things looks like. This is more about design engineering than production engineering. For physical devices, the effort of mass producing things is an enormous one. But that's not our problem, as we've already discussed. Instead, our problem is really focused on the design of things. And that's a very different, more exploratory part of an engineering discipline, and that is fundamentally our discipline. So I would argue that engineering is always at this level about exploration and discovery. So we could say that's true of our discipline too. Software development is about exploration and discovery. If that's the case, then what we need is that we need to be able to optimize for learning, and we need to become experts in our discipline at optimizing for learning. I have 5 ideas that I think are foundational to our ability to learn in this context. We need to work iteratively. We need to work in small stages so that we can evaluate our progress at the end of each of these stages. And if we discover that what we're doing is on the wrong direction, we can change direction. And if it's on the right direction, we can do more of that. But it gives us more opportunity to be able to choose our direction and steer our course towards success. In order for that to be valuable, we need to be able to gather feedback. We need to be able to gather information from our work that indicates whether we're making progress or not. And thinking about that and be thoughtful about the way in which we can carry out this iteration and learn from it. We want to work incrementally. We are not going to do all of the work to fully design our system at the beginning, expecting to have perfect foresight. Instead, we're going to proceed even when we don't know all the answers yet. That means we probably need to work a little bit more defensively. We need to be able to make work when we don't have all of the answers and defer decision-making to some degree. We want to be experimental. The kind of grandfather of learning really is science, and science starts from the assumption that we're probably wrong and then tries to find ways to show that we're wrong. That's part of working experimentally. That's deeply part of engineering thinking. The examples that I showed earlier of SpaceX building space rockets, SpaceX a year or 2 ago decided to switch the metal that they were using to build their space rockets to make them more efficient. They'd been using 4mm thick stainless steel, and they'd been building space rockets and even flying them at that point. And then they switched and they reduced the thickness of the stainless steel, same material but thinner, 3mm instead of 4mm. They still built a test piece and blew it up in order to be able to see what the failure point was with their manufacturing processes and the materials. So thinking experimentally, thinking about the ways in which things can go wrong is deeply part of an engineering discipline. And lastly, where engineering differs from science is that we need to be empirical. Empirical is about trying things out and seeing whether they work. Modern engineering for physical things, if you're building an aeroplane or a spaceship or a car, no doubt there's deep computerization and modeling of the problem. We'll simulate lots of things, but ultimately we'll then try those out in real circumstances. We'll fly the real aeroplane, we'll fly the real space rocket, we'll drive the real car. Software is the same. Our thoughts, our experiments are good, but we also need to be monitoring our systems in production and understanding them in real use and learning from that too. These 5 techniques are cornerstones of our ability to learn, and therefore cornerstones of any real discipline that we could refer to as engineering in the context of software. The other aspect of this is that software development, we build complex systems. And so part of professional software development is about managing complexity. We build systems that are beyond the capacity of any single human being to hold in detail inside their heads. So we must be able to work in ways that allow us to make progress when we can't perfectly predict the outcome of the entire system. So we've got to find ways of managing the complexity of the systems that we build. There are another 5 properties that I would call out that assist with that. These are related to the previous 5, but these form part of this model for thinking in terms of engineering. The first of these is modularity. We need to divide systems up into pieces so that we can deal with the pieces more independently of other parts. And to help with that independence, we need abstraction. We need to create seams or little lines of abstraction between the pieces of our system so that we can make changes in one place, understanding that this place interacts with another, but not caring about the detail of how that other place works. So each part of our system keeps secrets from other parts of the system. To do that, we can use separation of concerns, dividing the system up so that each part of the system is concentrated on solving just one part of the problem that we are faced with. And that allows us to improve the modularity and abstraction of our system and so on, and also helps us to start to decouple the systems, the parts of these systems, so that we can more independently change one part of the system without worrying about its impact on another. And the last of the 5 that will help us to do that is the idea of cohesion. You could think of modularity and cohesion as kind of compatriots. They're kind of opposite ends of the spectrum. What we want of a good system is that the parts of the system that are unrelated are far apart, and that's modularity. And the parts of the system that are closely related are close together. That's cohesion. All 5 of these things are tools that fundamentally play into our ability to be able to maintain our ability to change our systems as we learn more, as we get better ideas about the implementation of a system, as the problem that we're faced with changes, the business direction changes. These are all in companionship with the attributes of amplifying learning, are tools that allow us to sustain a constant ability to maintain and deliver new features and enhance the features that are already there in our systems, and hallmarks, therefore, of high quality software. So what are the principles of applying this kind of engineering thinking to our discipline? Well, we're going to optimize for learning and optimize to manage complexity. Part of that means that we need to start thinking a little bit more scientific in scientific rational terms, and in order to be able to do that, we need to understand the impact of our choices and changes and experiments. So we need to control the variables. We need to limit the impact of variables on our work. We want to make evidence-based decisions. We want to run the experiments and try out our ideas and start out with the assumption that any of our guesses about design or even the solution that we're trying to achieve are probably wrong, and therefore we should be looking for ways to falsify these ideas simply with more experiments to be able to understand these. Part of the reason why I'm talking about this is that in my career, I was involved in building very high performance systems, and we applied this kind of stuff to ultimately end up building what we believe is probably the highest performance financial exchange in the world. To get to those sorts of limits, you need to start thinking with these sorts of models. But this deeply impacts on the quality of software, whatever it is that you're building. One of the tools that we can use that enhance these properties is the idea of testability. And this will allow us to do a better job. So let's start about thinking about that from the perspective of what is it that we value in good code. And I warn you, this is going to sound rather familiar. Well, the first thing for good code is that it has to work. It has to do the job that we intend it to do. The next thing is that it's modular, so that we're able to work on it, and loosely coupled and cohesive and good separation of concerns, and all of those properties that we just mentioned that allow us to continue to be able to change it when the situation changes. Those are the markers of great code. So what is it before, in the absence of test-driven development, that allows us to do that? It's really only down to the skill, experience, and integrity of a programmer. Does the programmer have the skills to be able to build modular, loosely coupled, abstract systems with good separation of concerns and so on? Do they have the experience to have choices to make, to be able to, and in their toolkit to be able to make those things? And on the individual day, can they be bothered to apply those skills and experience? That's what it comes down to. Test-driven development is something very specific. And I think it amplifies our ability to achieve this. Test-driven development is often characterized as red, green, refactor. We're going to write a test and see it fail. That's the red step. We're going to do the minimum amount of code to make the test pass, and that's the green step. And then we're going to refactor the test and the code to make them elegant, beautiful, more generic, more fantastic, whatever it is that we want to achieve. That's the refactor step. Now, think about that process for a minute. We're going to start any piece of work, any change to our system, by first writing a test. We don't have any code yet. So what we're doing at this point is essentially we're designing the system from the outside in. We're trying to create a little specification that describes what we would like our system to deliver, our code to deliver. And if you're doing that, if that's where you're going to start as a software developer, you have to be a strange kind of person to make your own life more difficult. So what you're going to do at this point is you're going to try inevitably to make your own life easier. So you want to try and make it easy to write this test before you've got any code. So what that does is it applies a pressure on our code to be more testable, more easily testable. So what is it that makes code testable? Well, obviously it has to work, because what's the point if not? And then modular code is important for testability. We want to be able to test parts of the system in isolation from other parts, rather like SpaceX testing the rocket engines separate from the spaceship. We would like our code to be loosely coupled. We'd like to be able to test these pieces in isolation and not have too much work to get these pieces in isolation. That means that we'd like the pieces to be not too tightly coupled to other parts. We'd like the bits of, when we test our code, we'd like that to be definitive. If so we'd like the parts of our code that are closely related to be close together in the code. So in the scope of the same test, if something breaks, we don't want to be looking across lots of different tests. We'd like it to fail in one place and therefore be easier to work on. We'd like a good separation of concerns so that we can isolate these pieces more easily once again. And again, we need to exhibit information hiding so that we can evaluate interactions with other parts of the system without caring too much about how those other parts of the system really work, and maybe even fake them in the context of a test. So all of these attributes that we value as properties of high quality code, and that also seem to be hallmarks of an engineering discipline, are amplified by test-driven development. So that doesn't mean that we eliminate the need for skill, experience, and integrity of programmers. Of course not. But the combination of that skill, integrity, and experience with test-driven development amplifies our ability to deliver on these properties that we value in high quality code. So we get this kind of talent amplifier, and I can't think of anything else that really does a similar kind of job in software to test-driven development. This is not going to make a bad programmer great, but it will make a bad programmer better, and it will make a great programmer greater. And again, there's not much else that really does that in our discipline. So I would definitely say that this qualifies as being engineering. One of the attributes of engineering that I think is important, that if it doesn't amplify our chances of doing a better job, it doesn't qualify as engineering. So let's look at a little example of that, just to demonstrate what I mean. I've got some very, very simple code here. And what I'm going to do is that I'm going to make this code testable and nothing else, and look at that in the context of the impact of just that move on the code. So here's a car, and this car has a petrol engine, and it's got a function called start, where we're going to put the car into neutral, apply the brakes, and then we're going to start the engine. So let's write a test for this car. And here's my test: should start car engine. I'm going to create a car. I'm going to say start, and there's now nothing I can do. The engine's private. So without breaking encapsulation of the code, which we certainly don't want to do in any test, there's nothing here that I can do. This code is not testable. So let's start again, and let's start thinking about this from the perspective of making this code testable, and only that. So we're going to begin with the test. So should start a better car engine in this case. So we're going to start with what we really want to be able to do is we want to do this. We want to be able to say the engine started successfully. That's what we're really interested in. So that's our goal. And then when we start the car, that's when we want to know that the engine was started. So we can kind of write our test like this, and we can create a better car and provide the engine so that we can ask the engine this question. So there's my test. So that's set up some design decisions. And it's slightly changed some of these things. So I can create, in this context, a fake engine, which allows me to ask whether the engine was successfully started and give the fake engine to the better car. Yeah, this is just dependency injection. So here's my fake engine, just to show you that I'm not doing anything weird. We'd probably use mocks or something like that in reality, but I've just created a simple class here that does the same thing. When I call start, it just records the fact that start was called, and then afterwards I can ask whether it was actually started or not. It's that simple. Here's my code for the better car, and this is the thing that allows this test to pass. The change here between the better car and the car is very simple. It's really just this part. I've used dependency injection. I've removed the creation of the petrol engine from the car, and I've separated the concerns of the engine and the car more thoroughly in the better car to make my code more testable. Remember, I wasn't really thinking in terms of design. All I was thinking was in terms of testability. So what's the impact of this? Well, I've certainly improved the modularity, because now our code is just focused on being a car without worrying about the detail of being how you create a petrol engine. I've improved the separation of concerns, because now this code is only focused on being a car, and the engine is only focused on being an engine, and they're separate. They're in separate parts of the code now. This car is more cohesive. You could argue that it was cohesive before because it had all of the things that it needed with the car engine, but that's a kind of naive form of cohesion. Cohesion is about putting the things that are closely related and change together, and engines change independently of cars, or can do. And so, we can take an engine out of a car and replace it with a different engine. And now in our code, we can. So our code has better separation of concerns. It's more loosely coupled. Previously, we had to know how to create a petrol engine, and now we don't. We just need to know that there's a thing called an engine, and we don't really know any details about that. We don't even know that it's a petrol engine. Remember, in our test, we had a fake engine instead. And it's more abstract. All we need from this engine in the context of a car is the ability to start it. We don't need to know how to create it. So that's simplified all of those things. It's amplified just a little bit all of those properties that we were talking about as valuing. This is only by virtue of making our code testable. Now that, I think, is that is what I mean when I'm talking about applying engineering technique. By following this little discipline of test-driven development, what we have done is that we have designed better code. This code is better, not just in those sorts of abstract terms, in terms of modularity, cohesion, separation of concerns, and so on, but in practical terms too. In production, if I wanted to create a car, as before, I can create a car with a petrol engine, and that's exactly the same as the previous car. But I could also now create a car with an electric engine. This code is now more flexible than before. It will work just as before. We can test it better than before. And we can introduce different kinds of engines. If I was some kind of crazy person, I could even add a jet engine to my car. And still, this is working, and this is better code. It's going to be easier to work on, easier to test, easier to deploy, more flexible in production as a result of that tiny little change in focus of writing the test first. So that's what I mean by thinking in terms of engineering. What are those sorts of practices and techniques that we can use that will allow us to achieve better results? Another of those tools is to think about working experimentally. And experiments take different forms. We can think about these kinds of things, sort of tests as forms of experiments. We can do experiments consciously or accidentally that are going to cause failure and evaluate those. We can try testing with prototypes and all of these kinds of things as part of working experimentally. One of the key values of doing this, though, is to make progress in small steps. We want our experiments to be narrowly focused so that we can more accurately control the variables and understand what it is that we're learning from. That allows us to gather feedback and to predict the results of our experiments. This is not a heavily bureaucratic approach. We're not looking for kind of Six Sigma precision like a physicist. We're not physicists, we're software developers and we're engineers. So what we're looking is to apply loose versions of a scientific style of rationalism, but that don't get in the way, but amplify our productivity and the effectiveness with which we can make progress. And focusing on narrowing and controlling the variables. You can think of techniques like infrastructure as code or modularity as techniques for controlling the variables. Testing, again, drives our need for controlling the variables and results in software that is dramatically more stable and higher quality in production as a result. One of the ways in which I tend to talk about continuous delivery is this. It's a series of related feedback loops. We go from idea to releasable software. We use test-driven development as a fast cycle, and we use ideas like executable specifications to evaluate software at a slightly bigger picture view of a releasable unit of software. All this kind of boils into this kind of rationale of a more engineering-focused discipline. And this is a quote from a famous scientist, Richard Feynman. It doesn't matter how intelligent you are. If you guess and that guess can't be backed by experimental evidence, then it's still just a guess. So our job as engineers is to start just moving a little bit further away from guesswork, or at least putting the guesses at the start and then experimenting on them to validate whether our guesses are right or not. Another tool that I'd like to mention, which is maybe seem out of context here, is the idea of speed. Moving quickly drives good behaviors. This is a picture of two different cycle times from a traditional project and the project where we built the world's highest performance financial exchange. In the financial exchange, using continuous delivery techniques, we could make any change to our entire production system and get a definitive answer about whether it was releasable or not in under an hour. The more traditional approach, you get an answer is it releasable in the order of months? These are very, very, very different kinds of processes. So working to use techniques like continuous delivery to speed up the rate of feedback allows us to experiment more quickly on smaller scales with better control of the variables, and allows us to learn more quickly and create repeatable, reliable approaches to releasing software, and through automation, keeping nearly everything more controlled and more deterministic. And At the heart of continuous delivery is this. This is the idea of a deployment pipeline. A deployment pipeline is one fantastic platform for experimentation. We can inject changes in the form of commits into our deployment pipeline, and then our deployment pipeline's job is to determine whether our changes are releasable or not. So we're going to go from commit to a releasable outcome of some kind. In continuous delivery, we aim to do that all of the time. We aim to work so that our software is always in a releasable state. Now, to get there, one of the best techniques to do that is to focus on the speed of this feedback. How long does it tell you to determine whether your changes are genuinely releasable without there being any more work to do? So we can use that speed as a tool, as a measuring stick, as a benchmark of success. And there's good evidence that shows that working to optimize this process not only makes this process more efficient, it also increases the quality of the software that we produce. If you look at the state of DevOps reports, speed and quality are not antagonistic. They are actually reinforcing of one another. There's no trade-off between speed and quality. If you want to build high quality systems, the technique, the trick to doing that, the data says, is to build systems quickly in many small steps. And that's because we experiment, we can gather feedback, and we learn more quickly. So we can look to optimize all of this process. We can think about this part, and the goal usually that I recommend to my clients is that we are aiming to get this fast feedback in under 5 minutes to support development. And then the rest of the evaluation is looking at the releasability of our changes, whatever that involves, security, resilience, compliance, and so on. We're trying to achieve a releasable outcome in under an hour. If you can get to that, however it is that you do it, you're doing a great job, and you will see a dramatic improvement in the quality of your work and the efficiency of your work as a result of doing that. And what the data says, it predicts that the organizations that you work in will probably make more money and that you will have more fun while you're doing it too. These are the kinds of outcomes that we would expect if we were able to identify a real engineering discipline for software. We'd expect it to be better. We'd expect it to be able to produce higher quality work, because that's what engineering does. If you're interested in any of these ideas, I operate a YouTube channel, and there's lots and lots of videos on my YouTube channel talking about different aspects of this kind of engineering focus and the use of continuous delivery and other techniques to enable it. So do check that out. If you go to YouTube and look up continuous delivery, you'll find it, or you can look at this bit.ly link. Thank you very much. That's the end of my presentation. There's some links here if you'd like to catch up with any of my materials, and I'm available to take any questions for the rest of the time that we have. Thank you. I think you're muted.
Thank you, David. I always assumed that software engineers thought and worked like scientists, but I guess it's only starting to come to fruition right now. Great presentation. I myself learned a lot. I will have to say this, we're pretty much out of time, so I don't see any questions coming in currently. So why don't we just let you go and do your work. Thank you very much for your presentation. It was really interesting, especially for a non-IT person like me. I really enjoyed it. I learned a lot myself today, and I'm sure our audience did. Oh, we got a question. Sorry. I got one. At what level of detail must a request be in order to safely apply TDD? I always find unanalyzed scenarios that block me.
So the strict approach to TDD is that you don't write any code unless you've got a failing test. That means that you're going to test all of the behaviors that you can think of your code. Now, inevitably, we're human beings, so we're going to miss some stuff. We're going to miss some scenarios, but that's just true of engineering as well. And over time, what we do is that as we learn more things, we find a failure in production or something like that, we add more tests to cover the gap. So the goal is to try and drive the development process from tests. That's what the term test-driven development really means. So we only create code in the context of a test, and that tends to help us figure out what it is that we want. The skill to doing a good job of that is to try and make sure that the tests that we create are decoupled from the code. We want the test to express the need of the code, not how the code works. So we'd like our tests, our code, we'd like to be able to fulfill the need that's expressed in the tests by different versions of the code. So we don't want to be testing the implementation detail, which is one of the advantages of writing the test first, because we haven't got an implementation yet. So focusing on the outcomes, looking at those, thinking of those as little specifications for the work that we're about to do in code, works at all levels of granularity, at the finest level of detail, as well as at the level of whole features and ultimately whole systems. The systems that I worked on, we had tens of thousands, hundreds of thousands of tests that would execute and validate our changes on every commit to give us the confidence that we were ready to release.
Wow. Okay. Thank you very much. Last call for questions. Please submit your questions right now, or I'll have to let David go. Okay, David, thank you very much. Thank you very much for this presentation. Like I said, I truly enjoyed it, and I'm definitely a non-IT person.
Great.
Very good. Very good.
Enjoy the conference, everyone.
Okay, thank you very much. Bye-bye.
Bye.